So we had someone who's going to make an announcement about the robotics club. Are you here? Forget what is his name. Okay, very good. So let's. Okay, so I hope you have made more progress on the assignment by now. So again, go to the recitation today and make sure you ask all the questions. And if your questions are still not answered, then make an appointment to meet the TAs, right? So they have office hours, and so you should go to the office hours. Or my office hours are already passed for today. So if you want to meet me, then you'll have to send me an email and make an appointment. Okay, so I see the announcer. Okay, go ahead, Adit.
All right, yeah. So firstly, thank you so much, Professor Sakar, for letting me talk briefly during your class about the robotics team. And I just have a brief presentation that I'd like to give with some information about the team. So I'm not sure if,
Yeah,
I can. Okay, let me just pull it up. All right, so the Stony Brook Robotics team is, to keep it short, a multidisciplinary engineering team, club on campus that primarily, as the name suggests, works to design and build robots. But we also make sure to take on a bunch of other initiatives within our team that aren't just building robots or allowing you to work in the lab. We also provide a variety of workshops and seminars and programs that allow you to build your skills as a just engineer or someone who wants to go into the robotics field in the workforce. And that's what really differentiates us from just a run-of-the-mill club that allows members to just build something. We also teach you the skills that are really vital to build those, build robots or build engineering projects. And we also make sure to place a heavy emphasis on building a community within our team. So an example of stuff we've done in the past are monthly design socials, where we choose a mechanism to design in groups and then have fun doing so. And this semester, while everything is virtual, we've adopted monthly game nights, which we actually had our last one on Friday of last week, and it went pretty successfully. So we're always looking to ensure that members are getting something more out of being on the team than just building robots. We hopefully want to build a greater sense of, engineering prowess, but also belonging to the Stony Brook community. So to briefly go over some past projects we've done, we have worked on autonomous cars. We've worked on Mars rovers. We've worked on this robot that is like a tetrapod robot of sorts. And this year, we're also working on a project, albeit not building it, but primarily designing it for this semester. And you can find out more about the project that we're working on if you come to our general body meetings on Fridays at 3 p.m. And you can find more information about that either on SB Engaged or through some of the informational material that we have on our own website. So some important dates to keep in mind if you want to be involved on the robotics team or get a sense of what the team does. We have our general body meetings on every Friday at 3 p.m. And in addition to those general body meetings, we usually have workshops as well, which are designed, as I mentioned, to build your skills as an engineer, but also an individual who is looking to get involved in extracurriculars, but also be marketable when like applying to internships. So Python being a really important language that frankly, a lot of disciplines make use of in today's society. We have an Intro to Python workshop on the 9th as well. And we also have an Introduction to GitHub Workshop series starting next Friday as well. And if you want to keep in contact with the team and follow what we're doing, you can always join our Discord server, which you can access by scanning the QR code on the left. It's our primary way of communicating with members about what is happening in terms of events and projects. And on the bottom right are some QR codes to our social media pages. But that's all I have to say in terms of content. And thank you very much again, Professor Sakar, for taking the time out of your class to allow me to present.
Thank you for being here, and I hope you will convert at least some of the students to, look at activities outside the class. So it's great to work with your hands and do something that build things that actually move and do stuff, as opposed to just looking at the screen all the time. Okay, great. Thank you. So let's pick up from where we left off, unless you have questions well, he's already dropped out. Okay. Okay, so let's pick up from where we left off. And okay, so I know there are a lot more people in the class than the ones that I can see. So I want to ask you, I have mentioned this many times in the class that you should be looking at what's going on in Piazza. Why is it that only a third of the class has gone to Piazza? I'm baffled, right? It's not like I ask you to speak up in class. It's easy for me to say, hard for you to do. So I understand when people don't speak up. But if I say, look at Piazza and follow the articles there, if you don't even go there, I don't understand what what I can do. Do you know what I'm talking about? Have you read the course webpage? Right? If you go to Blackboard, it tells you, okay, just do these two things. And the two things it says are go to the course webpage, which I maintain, and then the Piazza site, right? And I have posted something about the exam, and only 24 people have viewed it, right? So am I to assume that the rest of you are not going to take the exam? Because if you're not ready, if you're not following up, and if you're not getting your system ready, which usually just means making sure that you have the right software, right? You have to download the right software. Then obviously you won't be ready for the exam. So I'm just puzzled. I understand that all of you just made a transition from high school to college, which is certainly a big challenge in terms of the academics, right? So now being asked to do a lot more on your own, uh, I think it's although my trip to college was almost 40 years ago. I still remember my first few semesters and how nerve-wracking it was to go from high school to college. So that is going to be a challenge, but I think keeping track of announcements and making sure that you follow the forum just seems like it's all of you are obviously it's not a lack of uh, knowledge or not knowing what to do. It just seems that you haven't done it, and I'm puzzled why. So from now on, whenever anything goes on Piazza, I want to make sure, if there are 56 people in the class, then I want to see, uh, you know, 60 people have watched, because it includes, five of us, right? So the instructor and, five other TAs, and then the students. So there are like 62 people that should be looking at the announcement. Uh, so please do that, right? So otherwise, you're just going to be left behind. You're going to miss an exam announcement, or you're going to miss what is included in the exam, or you might miss some sample midterms that I post. You're just going to be left out, and it's going to be uh, a costly mistake. So don't do it. Okay, so now let me talk about a few other things. So, uh, so we are, like at the halfway point in the course, right? So, and your midterm is going to be next week. There are a couple of things that I wanted to, remind you again. So one of the things in college is that you are expected to do a lot of work outside the class, right? So we spend uh, so for each hour you spend in the class, you are normally expected to spend at least 2 hours outside the class, right? So you should be spending about 8 hours outside the class, studying up the material, working on the homework, and so on, right? So this is not, I'm not saying this because I want you to, be an automaton and work hard all the time. That is not the point. The point is that, there is only, what I do in class is to try to expose you to topics and try to help you get started, right? But most of the work is on the part of the students, right? So you have to, you know, take that introduction and then take it upon yourself to actually follow what's being discussed in class. Look up on the internet if necessary. If, let's say, there is some math I'm saying that is not familiar to you, well, there is, tons of resources available to on the internet. You can talk to Google these days, right? I mean, what I mean is that you can type in just a plain English query and it comes up with pretty good answers to your questions. So really, you should be spending the time to learn the material on your own, uh, so that you're just not just relying on the classes and then say, hey, I should have understood it at the end of the class. That is not going to happen in this course or any other course, right? So it's always the case that in college we show the way, and and the students really have to do the heavy lifting. Okay, so that's something that I want to say. Again, keep in mind, every 1 hour we spend in class, you need to spend at least 2 hours on your own in order to keep on top of what's going on in these classes. Okay, and in programming intensive courses, well, you're doing most of that extra work becomes programming. But in a course like this, in a theoretical course where there is a lot of derivations and math and calculations, then that's the material that you need to be studying on your own. Okay. So okay, so let me just stop there. Are there any questions?
Professor, so I see the textbook has a lot of practice problems, but there doesn't seem to be any solutions to the practice problems. Is there anywhere you recommend we do practice problems?
So what I'm going to do is I'm going to hand out a bunch of sample midterms from the past. Okay, so you can work on those. You can also work on the sample problems in the textbook. But one of the difficulties is that this book was written for people in MIT, which means, well, the problems are going to be difficult, right? So one of the challenges is, how do you pick problems that are the right level? Because many of the problems that are there are not going to be problems that MIT students will be able to solve either, right? Or it'll take them, many days to solve the problem, right? So you don't want to do that. So let's look at these sample midterms that I hand out. In addition, you through the homeworks, you do have some collection of problems, right? So it's not, I have given you a fair number of problems when you consider not only the problems that you solved yourselves, but the others that the TA solved for you. So yeah, across them, I think you'll have enough to go on. Because when I set the homework, I do go through your textbook, right? And then whatever problems I find are at the right level and involve the right effort, right? So it's both the difficulty and the time it's going to take. Then many of them are already included in the homeworks that I give you, right? So it's going to be somewhat difficult to find more problems in the textbook. So just look at the midterms I hand out and maybe additional problems that I can give you, and you'll be okay. Any other questions?
The problem I found with the professor was that I would do the problems, but I wouldn't be entirely sure if I was right because there was no solution. Is there in terms of there being solutions to a problem, is there?
So this is sort of the policy that we have followed in the last 15 years or so of this course's existence, that we hand out past exams, we hand out problems, but we don't post solutions. And this is sort of how it has been run. And there is a good reason for doing that, because one of the problems is that it's difficult to generate good problems, and we don't want problems and solutions to end up on the internet. And then the result is that people who actually want to spend the time to understand and solve the problem, there isn't enough incentive because the solutions are already there. So this is sort of the reason why we haven't posted solutions, but the solutions, you can ask us, you can ask on, Piazza if you are not sure. So, this is, use some of the other means. I don't think we are going to be distributing solutions per se. Okay, again, when your homework is graded and given back to you, again, you'll see what mistakes you made. So that's the best we are able to do at this point. Any other questions?
Yeah, so the chapter we're doing today, is that on the midterm?
No. Okay, so obviously, we need at least 1 or 1.5 weeks lead time, right? Because we need to cover the material in class, hand out a homework, before we can expect you to, tackle that material in the exam. So what you will always see, except for the final, is that we will cover, the exam will cover the material that we finished up about 2 weeks before the exam. So any other questions? Again, speak up, please, because if you don't speak up, I don't know where you are. And, if you don't address the issue early on, then you will find that, you're totally lost, subsequently in the course. So, just, so we are, none of us are going to, so please come and meet us, right? Because you should really, whenever you have a question, talk to us. Again, use Piazza. Piazza is such a useful thing. It's just a, stupid, forum, right? If you post a question, then people can, you can help each other, and we can help you, and so on. So really, it's a great resource. Make use of it. Okay. Very good. So let's get started. Again, feel free to stop me anytime and ask me questions. Okay. So so today we're going to talk about sums and asymptotics. So see, often we need to so often we need to find closed form solutions for various types of series. So this is this sequence of 1 to n is something that we discussed in the very first lecture, and we showed how this is equal to, has this closed form solution. So if you have a summation like this, you can easily calculate it using this type of a formula, right? So these types of summations are things that you routinely come across in many fields. So as computer scientists, the place where this is most important is in algorithm analysis, right? So you are designing an algorithm, you're trying to find out how long it's going to take for this algorithm to run, right? And how do you figure it out? Because your algorithm has a bunch of loops and other things, and how do you figure out, how the whole thing is going to take time? And what you will end up with is often a sequence that represents how long it takes to run, something like this, right? And then you end up asking, okay, so how long, what is that? And then if you have a closed form expression, then you can say, hey, that's going to take n into n plus 1 times by 2 times, or approximately it's going to take time in the range of n square, right? So if I have if my input is 1,000, then it requires a million operations. If my input has million elements, then it's going to take a trillion operations, right? So you can do that by essentially dealing with these types of summations and figuring out what they add up to, right? They also come up very frequently in data analysis and financial applications. So for instance, this is what we call as geometric progression, right? So most of you either in calculus or some other course would have come across these types of progressions. This is called an arithmetic progression, or for short AP, and this is called a geometric progression, or for short GP. Okay, and we are going to, what we're going to do in this unit is basically look at some ways, some techniques for deriving these types of closed form solutions for summations like this. Okay, so the techniques themselves are going to be, some of the techniques are techniques that you can apply to new sequences that you haven't seen before, and there are other techniques where you're just going to say, hey, this looks interesting and nice, but it is not something that I expect to be able to apply on my own, and that's exactly what I expect. That is, there are techniques that you are exposed to, and you know that they exist, but it is not the kind of thing that you're going to necessarily use yourself. And then there are techniques which you will be able to use yourself. So we are not only interested in finding exact solutions to these kind of sequences. Most of the time, we are only interested in approximations, right? Because we don't want to know that this program will take, 237 seconds, right? So we want to know whether it's going to take a few seconds or a few minutes, right? So we are happy in computer science to live with a lot of approximations. So so what we are going to study is not only exact summation, but also approximating a summation. Okay, so this is called a Stirling's approximation for a factorial, right? So it's kind of interesting because you see a factorial. Factorial is a product of integers, right? So it's ultimately an integer, but the approximation formula has, all kinds of interesting things on the right. You have pi, right? And then you have the base of natural logarithm e. So a whole bunch of strange numbers show up when you are trying to find an approximate formula for n factorial. Okay, so it's kind of interesting. And what is very remarkable about this approximation is it's so accurate, right? So so most of these formulas become accurate as the value of n becomes large, right? So for small values of n, this won't be accurate, right? And many of these approximations become accurate only for pretty large values of n, maybe 100, maybe 1,000, maybe 10,000, depending upon the context or the particular approximation. But here, just for n equal to 6, already the error is so low, right? It's 0.1%, right? No, I'm sorry. So 1% at n equal to 6, and at n equal to 100, it becomes just 0.1%. So it's many of these approximations you can come up with are, can be quite accurate, and others are, still very, very useful for estimating because, many times we want rough estimates, and these are, very good. So let's start with something like a puzzle, right? So you want, let's say that you want a large, cash award, and the company that sponsored the award gives you the option of, one-time payment of $20 million, or they say they'll give you $1 million a year for the rest of your life. No, not rest of your life. Let's say forever, right? So which one should you take?
Forever.
Forever?
Yeah.
So tell me why.
Well, if you get 1 million per year, if you live past 20 years, you're gonna get 20 million eventually. And then if you're gonna get it forever, that means even after you die, you're still gonna get 1 million. So yeah.
Okay. So so what do people do when they have $20 million in their hand?
It depends on what you did with the money.
Right. So what do you do normally if you?
I mean, you could invest it, and depending on the return on investment, it could beat 1 million per year.
Right. So what is the return you need in order to beat that 1 million?
Well, I actually think the market average is 12%. So that's already better than 1 million.
Right. So you need only 5% to reach the 1 million. But again, don't bet on 12% because the market is crazy. So you should, if you look at so something like a 6% is a fairly conservative estimate. It's not too high. And so in order to make an informed decision, right? So what the discussion shows is that you need to sort of consider what is the return. If you have $20 million in your hand, what is the annual return you can get, right? And based on that, you can compare the two, right? You can say, hey, let me see after 100 years, what will I have if I get $1 million every year versus I have $20 million and then I invest it and I get a 6% interest every year, okay? So we could do that, but there is actually a clever way to look at the problem, which is instead of looking at how much you will have after a certain number of years, you can apply the interest in reverse and then ask, okay, what is the value of, $1 million I get next year in today's money, right? So suppose you get $1 million next year, then in today's money, that's what it is worth, right? Because at 6% interest, this much money, 1 divided by 106, will become this much, which is basically 1 million, right? So you multiply by 1 plus interest, right, to get the total amount after 1 year, right? So this is, suppose you had this much money, right? And then you have 6% interest, which means that in order to know how much you will have after 1 year, you should multiply it by 1 plus the interest rate, right? So some of you may remember this formula, multiply by 1 plus R for the total amount after 1 year and multiply by 1 plus R to the power n to figure out how much money you'll have after n years, because this is, what is called compound interest. But we don't have to know the formula, but we can work it out from first principles, starting from this idea that, $1 million that you receive next year is only worth 1 by 1.06 this year, okay? So what about the money you receive 2 years from now? That's only worth this much, right? And so on. Any questions? So if you want to estimate what is the total amount of money you will get in the future, you have to find this infinite sum, okay? So this infinite sum is nothing but a geometric progression, right? Because this is summation of x to the power I. So you can see that if you set x equals this value, and then you set I equal to 0, and then x to the power 0 is always going to be 1, right? X to the power 1 is going to be x, so that's 1 by 1.06. X square is going to be this, and x cube is going to be this, and so on. So what you have here is simply the summation of a geometric progression, okay, for which we already said we know the formula, right? We'll talk about later. I'll later tell you how we get this formula, but for now, right? So I already said, here is the formula for a geometric progression, right? So what is geometric here? Each term here is obtained by multiplying the previous term by x, right? So by a factor. That's why it's called a geometric progression, because the terms in this sequence, they increase by a factor of x, right? As we go from one term to the next, they increase by a factor of x. That's why, so this is called a geometric progression. So the values increase, geometrically, okay? So, so we take that formula, put it here, right? And because this is the infinite sum, so we take that closed form solution, which is for going from I equal to 0 to n. We simply substitute n equals infinity in this, right? And we get something like this. And notice that x is less than 1, right? So x to the power infinity is going to be 0, right? Any number less than 1, if you raise it to larger and larger powers, it's going to go to 0, right? And so you are going to end up with something, the numerator, this x power infinity, will just go to 0, okay? So, so therefore, the numerator will simply become 1, okay? And the denominator, notice that it's just 1 minus x, so 1 minus x is going to remain like this. And then I did the numerical calculation, it turns out to be 17.7 million, okay? So if the interest rate you can get is 6%, then today's value of an infinite number of annual $1 million payments is just 17.7 million, right? So the point is that when I asked you this question, the answer is, well, it depends on what the interest rate is, right? So what is the interest I can obtain? And if I tell you that the interest rate is 6%, then you can go ahead and calculate this and then say, hey, this is, you scammed me because, you're gaining $2.3 million by offering me terms that, look attractive to me, but in fact, it's more attractive to the person giving me the money, right? Any questions? So again, what you will see is that some of the steps here you may not follow, and I welcome you to ask questions and try to clarify. But it is also possible that sometimes it's just going to take time for you to look up some things, because not everybody's algebra and prior math knowledge is as current as others, right? So I'm quite sure that most of you have seen this in one form or the other. I mean, okay, what I mean is that the concepts I'm using are things that you have seen at some point or the other, but you may not remember everything quickly enough to follow every step. Again, I'm happy to explain, but if you don't follow, then you can also look at it offline and pick up things. So one of the things we should be able to do as computer scientists and engineers is to be able to ask questions like this and be able to answer them, because that's these are practical problems, and we should be able to solve practical problems by using by applying all the knowledge that we have. So have any of you have you heard the term annuity before? That term. Anybody heard of annuities? Well, these are not things that people your age worry about. Even people my age don't worry about it. People worry about it when they retire. So retirees, right, when they retire, they often have retirement savings, right? So that to ride them through the rest of their life. And one of the things that retirees often do is they purchase annuities. So annuities are things that are like pensions. They guarantee a fixed payment, every month or every year for the rest of your life, right? And the question is, there are companies that sell these annuity products. So people take $100,000 of their savings, give it to a financial company and buy an annuity from them, right? And then the financial company has to decide, okay, $100 million, I'm sorry, $100,000. With that, how much, monthly income can I provide without, running into a loss? And this is exactly the type of calculation that they use, right? So for instance, what this says is that to break even in a market that returns 6%, right? It says that to break even, handing out an annuity of $1 million a year, you need to price the product at $17.7 million, right? That is, if you take 17.7 million from someone at year 0, then you can keep giving them 1 million for the rest of their life, or actually for the rest of eternity, and still, that you will, that you won't be operating at a loss. And similarly, there are pension plans where it's increasingly rare, but there are companies that provide pensions to employees, and still a number of government organizations, right, provide pensions. And the question is, how do you figure out, because pensions are like certain fixed amount of money for the rest of the life of some employee, and how do you calculate how much it's going to cost to pay someone's pension, right? Because you have to, again, in order to give out a pension, the way a company operates is that they have some savings, they invest the savings, and based on the return from the savings, they pay out these pensions. And they need to figure out, okay, if I have 100 employees, each of them drawing, $50,000 a year, or $20,000 a year, then how much, money do I need to have in my savings in order to pay out all these pensions? And once again, it is this sort of calculation that goes into doing these things. So one difference, of course, is that most of the time annuity is not given forever, right? It's given typically for the lifetime of the beneficiary, right? So somebody bought an annuity, or somebody is eligible for pension, they get the pension as long as they live. And then, you don't have to make payments forever. You can say, hey, when this person bought it, their life expectancy is just 20 more years. And in that case, you can, plug that value 20 into the sequence, and then, again, apply our closed form formula, except that instead of infinity, which represents, payment forever, we are saying that there will be only payments for 20 years. And that yields this formula, which when you calculate tells you that it's, 12.16 million. So which means that once again, if you are going to give out hand out the annuity only for 20 years, then you need to charge only $12 million upfront, and then you can keep paying that 1 million per year. Okay, any questions?
Professor, could you just explain again what the 12.16 million, like what that means overall?
That means that if I put 12.16 million, okay, very simple, right? So let's say there's a bank that gives me 6% interest every year. Okay, so what this says is that if I put 12.16 million into the bank, right, and then each year, right, I take 1 million from the bank and give it to you. Okay, then at the end of 20 years, when I give you the 20th payment, right, my bank balance will be zero, right? But all the time, whatever is in my bank account, it's always earning the 6% per year, right? So that's relatively easy to wrap your head around, right? It's not a very complicated concept. You put it in the bank, it's earning interest as long as it is in the bank, and then every year you have expenses, $1 million expense. You're lucky you have a good life. So and then you deplete the money in 20 years, right? So what the 17 thing says is that if you are so you can also check if you calculate what is 16% of 17.7 million, it'll probably be just 1 million, right? So what that means is that you take the interest at the end of 1 year, right? And you leave the principal in place and you just take out the interest, right? So then that would be 1 million in this case, right? So this is why forever you can keep giving out 1 million, because your principal is preserved and you're just paying out the interest every year, right? That's why it stays forever. Here, it's not, your principal is not being preserved. Your principal is, decreasing every year, right? And that's why at the end of 20 years, you have zero, and then you cannot make any more, payments. Anyway, this is sort of the side discussion, because you're just trying to introduce summations using using an example. So let's look at how one would go about, figuring out what these closed form expressions are, right? So once again, if you have questions, if you're chatting with each other, answering each other's questions, great. But many times I'm not able to focus on even the mere fact that I take my mind off what is on the slide and try to talk about something else. I'm not able to do that efficiently. So if you have a question, again, please speak up and ask me the question instead of posting it on the chat. Okay, so one technique, right? So now we are going to talk about what are the techniques you can use to find closed form solutions for summations like this, right? So one technique is called perturbation method, which, as the name indicates, is not specific. It just says you tweak something and magic happens and somehow you get the answer, right? So if you have to make the magic happen in the exam, of course, it's very stressful. So don't worry, you don't have to do that, right? But it is, when somebody shows you the magic, then it's still interesting, like just like how magic itself is interesting, right? So we start with this, right? And we do a simple perturbation, which is to multiply this sum by x. So 1 is going to become x is going to become x squared, and x power n is going to become x power n plus 1, right? So we have We start with S equals, right? S represents the sum that we are trying to calculate, and S is the sequence. We multiply S by X and we get this, right? And then what we notice is that there are a lot of common terms, right? X, X squared, all of these terms are common, right? So if I subtract one from the other, then most of these terms will drop out. So I will have a very simple expression, right? So that's what I'm going to do. I'm going to subtract S from XS, right? And so most of the things will drop out. There are only two. There are two things that are, not paired up, right? So every other term is there in both S and X times S. So when you do the subtraction, all other terms will drop out and you'll be left with X to the power n plus 1 minus 1, right? And now you do factorize this, right? This is nothing but S times X minus 1, right? So this is nothing but S times X minus 1. So we keep S on the left-hand side and we take the X minus 1 to the right-hand side where it's going to go to the denominator, right? So we have X power n plus 1 minus 1 in the numerator. We leave it as it is, right? And X minus 1 goes to the denominator. And so we have the closed form expression we were looking for, right? Take a minute to look at it and see if you have a question. So it's called perturbation because what you're doing is you're trying to change something about the summation so that most of the terms would be canceled out, right? So that's why we did this, X times S and then subtract, then most of the terms cancel out, and then we just left with these two terms, which are not. So 1 is there only in S, and X to the power n plus 1 is there only in XS. And so when we do the subtraction, we are just left with X to the power n plus 1 minus 1, right? And that is the magic. And once we have done that, then the next step is elementary, and then we have this nice looking closed form solution, right? Of course, for many of these cases, right, it's when somebody shows you the method, it is quite elementary. It's not really, particularly complicated at all. But of course, if any of us were asked to come up with this, we probably wouldn't have, right? Because, how do you know that this is the kind of perturbation to make, right? At the same time, if I show you several examples of how this kind of perturbation is done, then maybe, right? Then maybe we can do some of these ourselves, right? We'll see. But but if you don't get it, that's fine. Still, at least we can see examples because the examples are still interesting. Okay, so now let's get back to, okay. So, so we showed how to apply this perturbation technique, which remember is not very well defined, right? It's not like a very specific technique. It says, do something to the sequence so that a lot of terms will cancel out, right? That's what perturbation says. And that's, not very, what is this thing that you do in order to cancel out? That's not specified, right? That's magic, right? So, but again, we can see examples of this magic, right? So let's go back to the formula that we already know, right? So this is n into n plus 1 by 2. We have derived this in multiple ways. But let's see if we can apply perturbation technique for this, right? And here is the idea, right? So what you're going to do, this is something that we kind of did in the first lecture. I explained it in a slightly different way, but it is effectively this. So we just write the same summation twice, except that we reverse the order of the terms in the second version, right? So once we reverse the order of terms, and then we can, sum them up, each of these, and you can see that it always adds up to n plus 1, right? Each of them adds up to n plus 1, right? Because they are reversed, it's always going to be, the two things, the corresponding terms are going to end up adding up to n plus 1. And how many such terms are there? So 1, 2, 3, up to n. So there are n terms, each of them having n plus 1 value, which means that 2s is n times n plus 1, right? And then we just take the 2 to the other side and we get s equals n into n plus 1 by 2, right? So in this case, we didn't really try to cancel things, right? Because if we did, then we'll get, 0 equals 0, right? So that won't help. So in this case, instead of making the numbers cancel out, we try to make them all the same so that we can combine them into a product like this instead of having, this, we start with n terms here, right? So 1, 2, 3, there are n terms. And we, if we make them all equal, then we can combine them into one multiplication. And that's what perturbation we were able to do this time. Okay, and now we have this, again, this closed form expression, very compact and very helpful. So there is another type of perturbation that I find very, very interesting, but of course, a bit more difficult, or I would say impossible to come up with unless you somehow, had a, I don't know, a vision or something. So sometimes what you do is that you start with, a seemingly unrelated sequence, and then you do something to it, and then you get to the sequence that you want to sum up. Okay, so let's see what this example, right? So once again, I'm interested in the very same progression, right? So this is the one that I'm trying to find the sum of, okay? But I'm not going to start with 1 plus 2 plus 3 plus whatever, but instead I'm going to start with summation of squares, right? So again, this is the summation notation, which says that I sum from I equal to 1 to n of I square, which is by definition this, right? So you set I equal to 1, then this is 1 square, that's what you get. Then you set I equal to 2, then you get 2 square. Then I set I equal to 3, 3 square, and so on. All the way to I equal to n, you get n square, right? Now, the perturbation I'm going to do is I'm going to now say, okay, let me look at I minus 1 square instead of I square, okay? And I fill it out. And if I equal to 1, then I minus 1 is going to be 0. So in this case, you start at 0. And then if you said I equal to 1, I equal to 2, 2 minus 1 is 1. So you get 1 square. All the way you set to I equal to n, then I minus 1 is going to be n minus 1. And so you get n minus 1 square, right? Now you can see that, hey, I have a lot of terms that are common, so I can do my subtraction trick, right? So I'm going to say, let me subtract this summation from that summation. Okay, so that's what I have done, right? So I square minus I minus 1 whole square. And when I do the subtraction, you can see that everything is going to cancel out, right? And I'm going to end up with just this term, which is not matched by anything here. So I'm going to end up with n squared, right? So I have done the simplification on the right-hand side, but unfortunately, I still have something complicated on the left-hand side. Okay, so what do I do? So here is our math trick. So you have this identity that says a square minus b square equals a minus b times a plus b, right? So you apply that to this, right? So you set a equal to I, b equal to I minus 1, right? So then a minus b is going to be a, replace the a with I, and I minus 1, which you can see is just 1, right? If you subtract I minus 1 from I, you're going to get 1. So a plus b, the same way, if you add I and I minus 1, then you're going to get 2I minus 1. Okay. So it looks like I have a mistake here. This looks like it should be a minus 1. Okay. But anyway, don't because instead of 2I minus 1, I have a 2I plus 1 here. But otherwise, so what I'm doing here is that I'm simplifying the summation using this formula, which is going to, right? So this is going to become I minus 1, 1. And this is going to become, so this should be minus, I'm sorry, right? So 2I minus 1. And so this should be 2I minus 1. And so then what I do is I just simplified this expression, and I got this. And then I basically simplify this further. And so so you can split something like that into summation x plus summation y, right? So it's not, you can so summation is because it's just summation being interchanged with summation, so you can do this. If this was a multiplication, then you cannot separate it like this. But if it's a summation inside, you can push the sequence summation inside, which is what I have done, right? And once that is done, then what I end up having is an expression that says 2 times sigma I equals right. Let's see here what exactly we get, right? So I still have the same, minus 1 error here, but the final term you get is n plus 2 times sigma I. Okay, so what we have here is this is the term for which we want to know the sum, right? Because this is the arithmetic progression, because if you look at what this is, summation I equal to 1 to n of I is nothing but 1 plus 2 plus 3 plus up to n, right? So this is the summation that we want the answer to. And what we have is we started from this, and we know that the whole thing is equal to n squared, right? So all we need to do is we set this whole thing to be equal to n squared, and then all we need is we do some so this must be, again, there is this sign mistake I made. So this should be minus n, so you should get n squared plus n, and then so you will end up with this answer, right? So so again, let's take a step back. What did we do? So we started somehow magically with summation of I square. We perturbed it so that we had a I minus 1 square, and these two steps are magic, right? So that somebody told you to do it, so you're doing it. But once you have done this, then you can see that the terms, if you subtract one from the other, then all the terms would cancel out except n squared, right? And then so you have this equation that says this whole sum is equal to n squared. And then you simplify this, and when you simplify that, you end up with an expression of the form that this summation of I, right, which is simply this sequence, equals n squared. And then the rest is just simplification, and the simplification gives you this n into n plus 1 by 2. So why did I go through this complicated method when I gave you this, very simple method for calculating this this sum? Any idea? Well, the reason is that this technique works to do the summation of any I to the power k, right? So for instance, if I am interested in this sequence, right? 1 power 5 plus 2 power 5 plus 3 power 5 plus 4 power 5. And I ask you, what is the closed form solution for this? Then you can apply this technique, right? So all you need to do is, instead of I square, you will start with I to the power 6, because you're interested in power 5 here. So you should go for one higher than the power that you want. And once you do that, you can follow the same technique, so which is worked out here for summing I square, right? And I'm not going to go through the steps because it's exactly the same as here, except for some algebraic simplifications, which are going to be a little bit different because, in this case, this is the identity we had to use. And here we will have this identity that we need to use. A to the power cube minus a to the power 3 minus b to the power 3 is this expression, right? So once we use that and then go through all the algebra, you will end up with the correct formula, which is this. I think some of you probably recognize that summation of I square, and others may not have seen it or may have forgotten. But that's how you can do summation of I square, or more generally, you can apply it to summation of any I to the power k, right? So so this is a little bit of as I tell you, it's magic, right? Because there's somebody had to tell you that these are the two you needed to start out with. But at least what you know is that, that technique works for, this problem, okay? And if you keep working on it, then you will ultimately come up with the answer, okay? And of course, the algebra gets more and more complicated as you go for larger and larger powers, right? Because there's just lots of terms. So if you go for a to the power 5 minus b to the power 5, does anybody remember what that is going to be? Anyone wants to guess what is a to the power 5 minus b to the power 5? So it has always the same structure, right? And then right, so when you have a to the power n minus b to the power n, it has always the structure, right? So a minus b times all these terms, which basically you list a and b with all possible combination of powers that add up to this number minus 1, right? So in this case, 4. So a to the power 4, a to the power 3, b to the power 1, that is 4, a square, b square, once again 4. So it's, but obviously now you will have so many terms, which makes it take a lot more time to do the simplification. And of course, we are going to make mistakes. And so it's going to be a mess. But the technique works. So if you have enough time, then you can do it. So I'm going to, we'll probably wrap up with this even more interesting example where we use differentiation, right? Differential calculus to do the summation, or we use differentiation as the way to do perturbation, right? So what is this arithmetico-geometric progression? It's one where you both increase by some number. So the coefficient, right, keeps increasing, right? So if you look at an arithmetic progression, that is 1 plus 2 plus 3 plus 4 plus, right? If you look at a geometric progression, it's going to be like x plus x square plus x cube plus x power 4, and so on. In an arithmetico-geometric progression, you are changing the coefficients this way and the exponents as in the geometric progression, right? So when you do that, you get this series. And the question is, can you find the summation of that? Okay. So we certainly see that it kind of looks like a geometric progression. So let me see if I can start with a geometric progression. Okay. So this is, again, the formula that I showed you on the very first slide, right? A closed form expression for a geometric progression. Okay. So now comes the magic, which is, this is not so much of a magic because, you can say, you know what? The term here is of the form I to the power xi, right? So if you think about x to the power I plus 1, right? And you differentiate that, right? Remember, what is the differentiation of so again, all of you, some amount of differential calculus is a prerequisite for the major, right? So you are either taking the differential calculus or you have done differential calculus in the past. So which doesn't necessarily mean you remember, but if you don't, you can easily look it up. This is why some of the working out has to be done on your own. But if you remember, this is the most common differentiation formula to remember. When you differentiate x to the power n, you get n times x to the power n minus 1, right? So this term kind of looks like that, right? So we say, hey, why don't we take this, and this is an equation, right? Whenever there's an equation, we can do the same thing on both sides of the equation. So why don't I differentiate both sides, right? So this is a function of x. This is also, the right-hand side closed formula is also a function of x. So why don't I differentiate both sides? And that's what we do. So, so if you differentiate x to the power I, you're going to get I times x to the power I minus 1, right? So that's why the differentiation of the left-hand side is quite simple. Now, the differentiation of the right-hand side is a little bit more involved because it's of the form, x divided by y. And if you remember the rule for differentiating x, divided by, well, I shouldn't say x to the power x by y. Okay, so I think I should use the, so if you have f of x divided by g of x, the way you do so there is a quotient rule, and I will leave it to you to look up what the quotient rule is and why, if you differentiate this, you will get this value, right? And for now, you can say, you can take my word that if you differentiate this, you get this expression. And once you get that expression, you simplify. After, here all we are doing is sort of rearranging the terms and doing the arithmetic. So, so for instance, so we multiply this, so that becomes n to the power minus. So we multiply this term minus nx to the power n minus 1 by this. So that'll give us minus nx to the power n minus 1. And then we multiply this by x. So that'll give us plus nx to the power n, right? And then we do this. And again, if you do this minus, 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 so that becomes minus x to the power n and plus 1. Okay, so this is what we have here, right? Plus 1 minus nx power n minus 1, and then this is I must have made a mistake here. Well, okay, anyway, so as I said, this simplification is something that you just have to do it, sit down and carefully do it. But there is no magic. Once we decide that we are going to differentiate both sides, then the rest is algebraic simplification, and it takes some time to do it right. But when you are done, then you end up with this closed form expression that says the summation of this arithmetic or geometric progression is this closed form formula, which certainly is more complex than the formula we had for geometric progression, which is just this, right? So that looks a lot simpler than this, but still this is much simpler than adding n terms, right? So so you do get a closed form expression that you can use for solving problems. So let me stop here. So what I want you to do is I want you to see that there are these techniques that are available for doing these summations. The techniques involve some, in many cases, they involve some magic observations, but in some cases they don't, right? So for instance, in this case, it's not so much of a magic because what is probably surprising here is that you have, you wouldn't have thought of applying differentiation as a technique for, doing this problem, because when you have equations, you often, you know, apply cancellation laws and take one term from the left hand side to the right hand side and so on. But the notion of differentiating both sides is something that's not common, and so that's the surprising part here. But once you notice that, then you are able to then the rest is just algebraic simplification, which takes time and but then ultimately you will get a nice solution, and then yeah, you're done, right? So so again, what I want you to remember at the end of this is here are the techniques for summation, and here are the results of applying those techniques, because formulas like this, and especially formulas like that, are extremely useful in computer science. You come across geometric progressions and arithmetic progressions all the time when you analyze your programs or algorithms, right? So you come across this all the time, and you need to estimate what the result is. And so knowing these closed form solutions is really important to do algorithm analysis. Knowing how to do the summations is also important, but obviously it's applied much less frequently, so it's not something that you do every day. Whereas something like this, applying this to sort of analyze one of your programs, is something that can be quite a frequent thing. Okay, so let me stop here, and I'm of course going to be here, and if anybody has a question, I'll answer it. But for the rest of you, take a short break and join your recitations. And again, let me ask you to make appointments with your TA or with me. So if you have any questions, you can go over those questions. Again, use Piazza, go look at all the articles, make sure that you're ready for the exam, and so on, okay? And in general, bring up any issue that you have. Okay, very good.